I think climate science is probably the most challenging science, especially due to politics, right? I just finished talking about the politics of elections and different perspectives. I think this is my perspective here. I think it's very hard for people to sometimes separate out opinion from science. Everyone has an opinion of climate change, but sometimes the opinion is not based on science. Sometimes it is. Sometimes it's based on incorrect science. And I think it's very challenging because there's the social studies part of this, where the question is, well, what do we do about this in the economic arena, in the political arena? How do we deal with infrastructure with climate change? But we always ask science to come up with the answers for us. Science will solve our problems. And you often see this phrase here, settled science. Everyone ever heard that come up before in terms of climate change? The science is settled, or the science is not settled. And that comes up a lot. That's the main focus of my lesson today. And to start off on that tangent, I want to discuss what makes something science. To make something a science, it should undergo the scientific method. And maybe you're familiar with this concept. Usually we kind of start here. You make an observation. It's hot outside. I think it's getting warmer. You think of an interesting question. Is the Earth actually getting warmer? And not just because of a season, but is the Earth getting warmer generally? Good question. Formulate a hypothesis. I think carbon dioxide is making our Earth warmer. And then this is something that all science requires. For it to be science, you're supposed to be able to develop a testable prediction. And I showed you yesterday that sometimes predictions don't always come true. Right? Like I showed you some predictions about how we have 5 years left to save the world, and that was back in like 1990 or 1989, right? There's the person who thinks the world's going to end in 10 years, and they're probably going to be wrong about that one too. That doesn't make it so that science is invalidated, though. Just because one prediction goes wrong doesn't mean you throw out the entire science and say, oh, well, it's all hokum. Here's an example that I use a lot. If I were to drop object A, it'll fall. If I dropped object B, it'll fall. If I dropped object C, it'll fall. I'm making a prediction. I think that objects fall because of gravity. And then I take out a helium balloon. Does the helium balloon fall? No. Did I just disprove gravity? No. And that's the point I want to make, is that when it comes to climate science, a lot of people, if they find one piece of evidence that doesn't support what they are hoping to be true, sometimes they like to ignore that. And they go, well, let's just not talk about helium balloons. You're a gravity denier. Well, yes, there's some people who are denying, but I think we need to be able to have an honest conversation about what science requires, because it requires predictions. And when you eventually gather some data, like in my hypothetical example, I dropped objects on the ground, sometimes you need to refine, alter, or expand your hypotheses. And by its very nature, science is supposed to be an ongoing process. By its very nature, it's supposed to continue to happen. Why do we still teach about biology and physics and chemistry? Most of those sciences we would consider to be quote-unquote settled. There's not really a lot of debate in the chemistry world. We believe that there are subatomic particles. We feel like we fully understand how protons, neutrons, and electrons are there. So why do people still study chemistry? Well, because there's still more to learn. Right? There's still more that happens. Sometimes you have to refine, alter, or expand what you're working on. And I think this last one right here is what causes so much problems with climate change, is the word reject. Because just because you reject one little idea doesn't mean you throw out everything. You get where I'm going with this a little bit here? And rejecting poor ideas is supposed to happen in science. It's supposed to happen. It's a natural part of the process. Okay? Which then comes to my personal opinion on this. I really don't like the idea of ever there being a settled science. I think that's an oxymoron. You guys ever heard the term oxymoron, where you put two words next to each other, but they're kind of opposites of each other? Yeah. Yeah. Science, by its very nature, should not be settled. I guess it depends on what you mean by settled. If by settled you mean that you're not allowed to reject things ever, then it can't ever be science, because by its very nature, science requires refining, altering, expanding, or rejecting. And let's say, though, that you say, Chris, this was an optional loop right here. You say, Chris, you don't necessarily need to do that. Well, the way that science is supposed to work is after you test hypotheses, you're supposed to develop a theory, and then you're supposed to make more observations. You might notice there's an arrow right here. You're supposed to keep going. Right? So by its very nature, science requires that we keep searching and seeking. We don't ever just stop the argument and say, I win because science. And yet that's what most of the grown-ups right now do. They say, my side is right or your side is wrong, and all political parties do this. Again, not a social studies class, but all political parties do this. And they like to just end their answers with, because science. Right? That doesn't work. Here's another picture that I like that describes what science is supposed to involve. You find a problem. I think our Earth is heating up. Polar bears are losing their habitats. Sea creatures are having to migrate. I don't know, pick an answer here. Form a hypothesis, make some observations, organize some data. Then you ask the question, do experiments and observations support hypotheses? There's a lot of people who don't like to go down the no pathway because sometimes your experiments and observations don't support your hypothesis. And that's okay. The point I want to make is that that doesn't disprove the entire science. Okay? It sounds a little bit like I'm trying to tell you that climate change is not real. That is not what I'm saying at all. Let me come out clearly here. The greenhouse effect, in which I've already kind of explained to you how carbon dioxide causes more heat to be absorbed by an atmosphere, I believe that to be a fundamental physics principle. But yet there's a lot of things associated with climate change where it's a little in that wishy-washy territory. And when the answer is sometimes no, we have examples of scientists who decide to just ignore this data and they go, ooh, I got a result I didn't want. Let's just crumple up that sheet of paper and throw it away and pretend it never happened. That's not how science is supposed to work. We're not supposed to be afraid of the no. We're supposed to be willing to circle back around and say, let's try again. In the same way that when my helium balloon rises, I don't call somebody a gravity denier. I say, okay, I got more work to do. I got to explain, why did this happen? That makes sense? Okay. I love this cartoon. This is a cartoon series. It's by Nathan W. Pyle. I forget the name of the cartoon. It's about little aliens. Maybe you've seen it before. This one's perfect in my opinion. The alien who's not native to Earth, but is exploring Earth's culture says, I have attempted science. And the larger alien says, please explain. I formed an idea, and then I discovered I was wrong. And the older judge alien says, there are numerous diagrams. And the guy says, I was wrong in numerous ways. I produced a detailed tribute to my wrongness. And he has one of those classic, science fair sort of things there, right? And then this guy says, that is science. And I agree with him. That's what science is supposed to be. I think we do have disservice to students when we teach them science. Especially, have you guys ever done science fairs before? Oh, I mean, the best science fair projects, in my opinion, the very best ones. Hey, Vic, what's up? Hi, how can I help? Okay. Sorry, I'm right in the middle of a class. Do you need something? Oh, is this your stuff that's here? Yeah. Okay, here you go. Oh, you can leave it in here, but I need you to take off, though, because I'm right in the middle of something, okay? Okay, we'll keep going. Where was I? You guys have done science fairs before, right? I don't think we judge science fairs the way we should. We should judge science fair by the student who spectacularly fails. And I don't mean fail by doesn't do their project, by the student who tries something and it doesn't work. Because that's how science is supposed to evolve and develop over time. We've talked about Dyson, right? How Dyson, they model their air conditioners and their vacuums based on how many failed prototypes they need. That's how science is supposed to work. I have a timeline on the board over there behind Harrison that is basically the history of physics. And one of the things that I really try to teach my physics students is that science takes a long time to develop. There are many failed models. In 1803, John Dalton suggested that an atom was a solid sphere. He was very wrong. And scientists did not figure that out for almost 100 years. And that's okay. I don't blame John Dalton. I don't say that John Dalton was a horrible scientist. It's just he knew what he knew at the time. Okay. So that's kind of my preamble before I start here. Okay. You good to go? Yeah. Okay, we'll see you later. Hey. Here's some words that I'd like you to know. Again, not because it's on a test, not because you're being assessed on this, but I think it's worth knowing. The words are called empirical and theoretical. And there's two types of research that scientists do. Okay. Empirical research basically means you're doing a lot of observations and data collection. This would be the person who drops object A, drops object B, drops object C, and discovers, hey, I drop things, they fall, based on data and observations. But for something to be science, you also need the theoretical side, which means you need to create a theory based on logics, explanations, and since I teach physics, I really like to use the word principles. We need to have a principle like the law of conservation of mass or the law of gravity, something that we can then explain with a theory. Does that make sense? Yeah. Yeah. Yeah, Schrodinger is the guy who we often attribute to starting the quantum model, but he's not the only one. Yeah, you're right, though. We didn't actually talk about Schrodinger. Why don't I hop to that, though? Okay. These are models of the atom, right? Which are somewhat based on data collection, but also somewhat based on just logic and explanations. At the time, J.J. Thomson's logic was that he thought it was a positive pudding with negative electron bits. And that was his model that he made based on the evidence he had at the time. I would suggest that if you want to use the word settled, which I really hate to use in science, but we could probably say that it is settled that subatomic particles exist. Although, to be honest, who knows? Maybe in 50 years from now, we'll discover that we were spectacularly wrong about that too. I doubt it, but it certainly hasn't. It's not like it hasn't happened before in science. But here's what's not settled. The nature of the cloud model. This whole concept of Schrodinger and other scientists who try to figure out where are those electrons, scientists are still working on that. So is chemistry a settled science? No, it can't be, right? There are some things that I think we probably know for sure, but what is for sure in science? All it takes is us discovering one new thing and we discover, oh my goodness, we were wrong about that. It's happened. I like this picture here. This is how knowledge should be developed in a scientific realm. There should be the theory and the practice. The vocabulary I want to change, though, is that practice is sometimes changed to the word empirical. Empirical basically means you're talking about observations. You're talking about data. Something that you can collect. Theory is more about developing a model. It's more about coming up with physics principles. Does that make sense? But ideally, those two things should be intertwined. Ideally, one supports the other. They both work hand in hand. Okay. One more thing, when you're doing experiments, I'd like to also remind you of what good research methodology involves. The word that we want to use is called a controlled experiment. That's what ideally science should involve, a controlled experiment. And I'll use the vocabulary in a second. Let's just use this picture as an example. Let's say that as a scientist, you want to prove that caffeine influences how many words a person can recall. I found this picture online, so just to go with the example. If you drink more caffeine, you have a better memory, I think is more or less is what this is suggesting. Okay, so she just said, if no one heard that, why am I doing bad at science? First of all, no one's doing bad at science. Okay. But let's change it for another topic here. There's the other variables too. A controlled experiment tries to isolate just one thing that we want to know about. And that's really hard to do in science. Because let's say you do an experiment, you do a study, and you give certain people pop, coffee, tea, different caffeinated beverages, and then you test them on how many words they know. But there's other things you should consider, like say the time of day. We start our school at 8 o'clock in the morning. How many of you are at your peak optim performance at 8 o'clock in the morning? You're just like, ready to go. As a silly little example, but hopefully you'll understand this one. My Vancouver Canucks hockey team, that's the team I cheer for, just finished an East Coast road trip where they had to play New Jersey and New York. And the NHL, in their infinite wisdom, scheduled it so that both of those games started at noon, local time. You know what time that is for the Vancouver bodies? 9 in the morning. So the Vancouver players, their bodies think it's 9 in the morning, and they're playing a game that's local time at noon. Most of the time, hockey players play in the evenings. By the time they finished their second game, you could tell Vancouver was just exhausted. They were bagged because they weren't playing when their bodies are conditioned to play. Does that make sense? Now, the point I want to make is that there are other variables. If I were to watch one game, you might conclude, wow, Vancouver is out of shape. They need more conditioning, or they're a bad team, right? Unless you get a little context and you realize there was another variable we didn't consider, time of day. Right? Here's another variable, at least for this little experiment here. Let's say you're trying to remember how many words you're recalling. Let's say it's really noisy. Some people don't really do well in a noisy environment. Right? A good experiment, then, tries to control variables, sorry I didn't draw that very well, by removing all other possibilities. But it's really hard to do that sometimes in science. It's really hard to make it so that only one thing is being tested. the vocabulary that I'm hoping you're somewhat familiar with is that the independent variable, we often call that the manipulated variable. Manipulated. So we change how much caffeine we give somebody. The dependent variable is what we sometimes call the responding variable, if you've ever heard this terminology before. It's basically what you've discovered the manipulating variable causes. And then the controlled variables are ideally everything else. So if you can control every other option, hopefully what you can prove is that caffeine leads to more words being recalled. But we have to make sure that time of day isn't an issue. And so if you feel like you're not very good at a class in school, it could just be because it's early in the morning. Right? There are other variables to consider. Okay. Here's another thing I want to talk about when we talk about just the nature of science, before we get to more of the global warming stuff here. With the advent of technology, it's now fairly easy for some scientists to collect massive amounts of data. And sometimes what we call science is better described as statistics. Okay. The scientific method requires data collection. Let me go back here again. The scientific method requires you to collect data. That is supposed to be something you do as part of science. However, there are some scientists who that's all they do. They just collect data all day. They don't make observations, because they don't do any experiments in that sort of way. They don't think of interesting questions. They don't develop testable predictions. All they do is they just gather as much data as they can. And the point I want to make here is that that's maybe not so much science, that is statistics. I've got a couple cartoons I want to show you here. Here's the first one. This is Dilbert, if you haven't seen Dilbert before. I didn't have any accurate numbers, so I just made this one up. Studies have shown that accurate numbers aren't any more useful than the ones you make up. Hey, how many studies showed that? 87. If you kind of get the joke, he probably just made that up right off the top of his head. Right? Because sometimes statistics, people just lie about them to try to prove their point. That's actually the point of my next cartoon here. There's a famous quote by a guy named Benjamin Disraeli. He said that there are three kinds of lies. Lies, pardon my language here, damn lies, and then worse than that is statistics. Anyone ever heard that before? Because sometimes you can use statistics to prove whatever you want to prove. If you have enough data and you know how to manipulate it properly, you can honestly sometimes prove anything. Anyways, the cartoon goes on and says, 9 out of people say that was Mark Twain. And then this guy says, there are 3 types of punchlines. Obvious, painfully obvious, and he adds, I thought the Twain bit added an extra layer. Maybe this better illustrates my point. I like this cartoon right here. Here's the guy. He says, as you can see, by late next month, you'll have over 4 dozen husbands. Better get a bulk rate on wedding cake. Because yesterday, this person wasn't married. Today, they have 1 husband. Based on, quote unquote, the data, tomorrow, what's the trend? Tomorrow, you'd have 2 husbands. And the next day, you'd have 3. Yes? Great point. And here's my point here. Here's my point. There are some people in trying to make an argument and trying to win an argument, there are some people of all political affiliations and all opinions who like to there are some people who what they like to do is they like to call the data science. But I think this is an extreme example, obviously. You guys would not call this science. That was crazy. And yet, whoever's talking, can you please knock that off? Because I've got a lot more to cover today. By its very nature, science is supposed to have predictions. By its very nature, science is supposed to have a prediction. And so someone might argue, well, this was science right here. Science says that tomorrow you'll have 2 husbands, the next day you'll have 3. By the way, if you don't know this word here, extrapolating is a fancy science word for making a prediction. And we like science to make predictions for us. We want science to tell us how to inform our actions. We want science to tell us, here's what we should do. Right? But then the struggle is, we got to make sure we're actually looking at science and not just statistics. Does that make sense? I think this example is an extreme example here. Here's a couple more vocabulary words I want to share with you. The words are correlation and causation. I've already tried to share this concept before. As a recap, correlation is where there's a statistical relationship between 2 variables or events, and it may indicate there's a link between the 2. Causation, though, is evidence that one event is the direct result of another event. And if you don't feel like you get the difference between the two, I want to share with you this study I found to help illustrate my point. You see this in the newspaper. This is in the Telegraph. This is a British newspaper. Dark chocolate lowers the risk of depression, British study finds. And so everybody goes, I should eat more chocolate. I'll become less depressed. The headline talks about correlation. The headline says, if you eat dark chocolate, you will be less depressed. That headline suggests correlation. Read the subheadline, though, and let's dig a little bit deeper. It says, while 7.6% of the 13,000 people surveyed reported depressive symptoms, just 1.5% of the chocolate eaters did. This top headline is an example of causation, and I don't think the causation is true. The bottom one right here is correlation. Okay, it looks like we surveyed 13,000 people. 7% of them were depressed. And as we collected a massive amount of data, we happened to stumble into the idea that, hey, only 1.5% of these 13,000 people, only 1.5% of them were depressed if they ate chocolate. But does that mean that chocolate, for sure, causes a lack of depression? I don't think the study proved that. They just happened to find some similar things here. And here's what I wrote down here. Did they prove that dark chocolate protects against depression? Or what's probably more likely, are depressed people just less likely to choose the healthier chocolate? Do depressed people perhaps eat lots of chocolate, but they just don't eat dark chocolate, they eat milk chocolate, they eat caramel? I don't know about you guys, but I don't like dark chocolate. It's very bitter. Some people consider dark chocolate to be maybe the healthier chocolate variety. And so perhaps, people who eat dark chocolate are also a little bit more health conscious. And by being more health conscious, perhaps they exercise more. And because they exercise more, they also happen to have more positive, what do we call them? Brainstem, what do we call them? Hormones, there we go. Being released into their brainstem. And so the positive ones, what are they called again? I'm totally blanking. Serotonin, there we go. That's a good example one, right? Some of those hormones that cause you to be happy, perhaps you're more happy, and therefore you don't report depression. Do you get the logic I'm going with there? And so perhaps both the dark chocolate and the lack of depression are just symptoms of the same thing. Maybe this is just somebody who exercises more and is more health conscious, and it just happens to be the same. Here's another example. Okay. Say you go to a store, and the store suggests that they always sell a lot of sunglasses when they sell ice cream. And so they suggest, sunglass sales drive ice cream. Except that maybe that's not really what it is. Because maybe what's really happening is, why are you selling a lot of sunglasses? Because it's sunny outside. And why are people buying ice cream? Because when it's sunny outside, it's also hot outside. Did the sunglasses actually cause the ice cream sales? No, they just both happen to be somewhat related to something else. I think this study suggests that. You see the study title, and you're being misled into believing something that's science, and so you go, Mom and Dad, I need to eat more chocolate. It's not going to let me be depressed, and that's not what the study said at all. You get why science can be really challenging here? Is that we need to teach you, as students, how to have a good ability to decipher the junk science. And this is junk science. This should not have been posted on a science page, because this was just statistics. There's no actual, remember how we talked about empirical and theoretical evidence? There's no theory behind why dark chocolate causes depression or lack of depression. We just said that it looks like there's some stats. That doesn't count. That's not science on its own. It's part of science. Here's my point. Now we're going to talk about global warming for a little while here. This is the classic graph. You've probably seen this before, where on one axis you put temperature, one axis you put CO2. Carbon dioxide seems to be going up. Temperatures seem to be going up. This is only correlation, though. This is not causation. If someone were to be having a climate change debate and they were saying, look at the data, what I want to teach you guys how to be able to do is to say, but that's not enough to be considered science yet. This is just a graph, whereas one goes up, the other one goes up. It may be causation, but as of right now, it's just a correlation. Let me show you some other examples of some graphs that, if used incorrectly, could be used to prove something. This is kind of silly, but here's a graph of per capita cheese consumption with people who have died become tangling in their bed sheets. Would you suggest that people who eat cheese more are more likely to die by being tangled in their bed sheets? Well, according to the data, look at the science, people. It's irrefutable. As one goes up, so does the other. Class, that is not causation, that's correlation. We've discovered that by some random chance, both of these things go up at the same rate. But hopefully you'd agree, there's no link between these. Here's another one. U.S. spends more money on space science and technology. Shh. Suicides by hanging, strangulation, and suffocation. Sorry about the subject matter, but you'll notice that they seem to work with each other. Do people hang themselves, strangulate themselves, and suffocate themselves because the U.S. spends more on science? I think most of us think that's probably a silly link. Here's the point I want to make. This is why I started the lesson the way I did. I'm not suggesting climate change isn't real, but I'm suggesting that if someone is using this as an argument for global warming, that's not okay. That's not sufficient. This is just the data. We need to do better than that as scientists and as students who need to understand how to use this in our world. If I could go back to the slide here that I gave you about the silly one of the person in the wedding, why do we like to have charts like that? We like to have a chart so that we can say, based on historical data, here's my temperature, and I would like to predict that it's going to keep going up. But here's the problem. Was that a fair assumption in the wedding example to predict that it would continue on that rate of growth? That's one of the fallacies of just using stats. Now you might argue, Chris, these are just lines that are going up. I bet you could find lots of lines that just slightly go up, and you can relate any two variables. But I mean, here's some more interesting ones. There's a website, by the way. If you like looking at some of these crazy things, there's a website that has a whole bunch. Here's a number of letters of the winning word in the spelling bee and people who are killed by spiders, venomous spiders. And like, look, it goes up and down, honestly, the exact same. Two things that are definitely not, there's no causation between the two. And yeah, we proved correlation. This is my favorite one. How many films Nicolas Cage appears in a year? And how many people drown by falling into a pool? There's no correlation between Nicolas Cage being in movies, no matter how bad they are, sometimes, and people drowning.
Well, think about it. Nicolas Cage is in a cage, and if you're in a cage, it's safe people not drowning.
Whoa. All right, let me keep going though, because I got lots more I want to talk about today. This is an interesting topic, by the way. I hope that you're finding this useful and a good thought process to walk through. The theoretical science of causation between greenhouse gases and temperature change has been well established. That graph I showed you 2 slides ago, the one where I told you that this is not sufficient, I believe that this is not enough to be considered evidence for climate change. But the good news is we have more than that. We have the theoretical explanation. We know, theory-wise, that infrared radiation causes molecules to vibrate, and molecules vibrating is literally the definition of heat. And so therefore there's temperature increases. Quick recap, because this is worth knowing. What do microwaves do to molecules? Microwaves cause molecules to rotate. Perfect. Like water in the microwave, yeah. Infrared causes molecules to vibrate. Visible light causes the electrons in atoms to jump to the higher levels. And ultraviolet light has enough energy to cause the electrons not just jump to a higher level, but we photo emit them, and those are the electrons that solar panels use to make electricity. Okay? We have a theoretical basis for carbon dioxide and heat temperatures. And so here's my point, though. Is the science settled? Well, that part of the science we seem to have figured out pretty well. Remember that tree that was intertwining there? That's a pretty good tree. Yeah, feel free to close the blinds as we need to, by the way. Okay. But new research still needs to be done because what do we need? We need those predictive models. Science requires us to make predictions. Here's the challenge, though. We have a very sophisticated and complex ecosystem. Our biosphere is not an easy thing for us to make predictions on. When is the next earthquake going to happen? Do we really know that?
Yes.
When is the next hurricane going to show up? Like, do we have this planned out where we can go, like, we know this with certainty? Our Earth is such a complex place. There are so many variables. It's hard to know a lot of these things for sure. Remember the idea of controlled manipulating responding variables? It is very hard to control every variable on Earth when we're talking about science because there's so much. What does the atmosphere do? What does the sea do? What do plants do? What do humans do? There's just too many things to consider sometimes. Okay. Here's a picture, though, that I think helps to reiterate, though, what we know, or at least what we think we are fairly confident about when it comes to the theory behind climate change. Here's the incoming radiation. Let's just call it 340. We know that if there's more radiation coming in or less compared to what's going out, add these two numbers here, right? You've got 100 and 239. That adds up to 339. See that? 100 is going out, 239 is going out. What's 100 and 239? 339. You have 340 coming in, 339 going out. What's that going to do? In theory, this should increase our Earth's temperature, right? This is a very theoretical explanation of what is happening. The graph is an empirical explanation of what's happening. Okay. Here's a Bill Nye video I want to show you that kind of helps to illustrate the same things we're talking about here. Aaron, can you do me a favor? Can you close those blinds over there too, actually? Thank you. There you go. I had too much glare. I can't even see my video here. Okay, listen up, okay? Shh. Okay, let's do a quick little recap of that. So here's what Bill Nye explains here. So he's got two jars. What is he trying to control so far? Well, they're the same size, right? Same shape. We don't want to have anything be different. Puts the same globes inside as a representation, covers them both. But what does he manipulate? In one experiment, he puts inside some extra carbon dioxide gas because of this little tubing that he puts inside, right? So that is ideally the one manipulated variable, right? Then we put the carbon dioxide inside. We're controlling the amount of heat. So both of these heat lamps that are emitting infrared, they're ideally the same as each other, same distance apart. And what's the responding variable? As we look at the thermometer, one of the thermometers goes up higher. This is known as the greenhouse effect. And it's been a well-researched, well-proven, girls at the back, please. I've looked at you a couple times here. Give me your attention, please. This has been a well-researched phenomena that we would basically say is on par with like what we understand about gravity. We understand this concept. Okay. Bill Nye then goes on to not just do experimental data, but to then give a theoretical explanation of what's happening. Do you guys see those two words there? One was experimental data. One is now a theoretical example. Okay. I thought he did actually a really good job on that particular video. I will show you one in a bit, though, where I don't like his explaining of science. No, I do, but I do think that there's some times where I think he could do better. All right, let me keep going there. I got lots to cover here. Here's another graph or image that can help explain what we know about the carbon dioxide effect. Here is in color up here at the top. Ultraviolet light is downgoing solar radiation coming in through the atmosphere. We get some ultraviolet light, we get some visible light, and we get some infrared light, all from the sun. Right? That's basically what this is saying here. This is transmitted to us from the sun. However, we're supposed to have some thermal radiation go back up, and it leaves in the infrared. Why? Well, because everything on Earth is made of molecules. Molecules vibrate, and vibrating molecules give off infrared. You and I and everything in this classroom is giving off some infrared. Ideally, some of it goes back again. Here's the point I want to make. Scientists have been able to figure out where carbon dioxide falls in the spectrum. carbon dioxide absorbs, see the absorbing part right here, in this area, here, here, and here. There are 4 specific locations where carbon dioxide does absorbing. Carbon dioxide does not absorb red light. You know what absorbs red light? Yellow objects. Let's talk about that again. Why is red light absorbed by a yellow object? Because what color is reflected by a yellow object? Yellow, which means all the rest of the colors are absorbed, right? Right? So blue absorbs red, and white reflects. Does that make sense there? So what does carbon dioxide do to red light? Nothing. What does carbon dioxide do to X-rays? Nothing. What does carbon dioxide do to blue light? Nothing. What does carbon dioxide do to this particular section of infrared? It absorbs it. What does it do to this particular section of infrared? It absorbs it. So we've discovered that there are 4 specific sections of infrared that carbon dioxide is able to absorb. And I think I showed you guys in the past that carbon dioxide can kind of wobble up and down or side to side, and depending on which one of those happens, depends on what gets absorbed. Okay? Here's the follow-up question, and this is what scientists would like to know. We currently have a graph that says here's our temperature, here's our carbon dioxide, and we're going to say, what if we keep adding more carbon dioxide? If we keep adding carbon dioxide, the question is, what's going to happen to the temperature? But here's the problem. Is it fair to just assume that because it's always been in a straight line before, that it will continue to do that? Because I just showed you in that really extreme example of a person getting married, just because it happens for the first time or the second time, does that mean for sure it's going to continue? Because again, that's only experimental data. We need a theory to describe it. And the best way I can describe that for the theory is actually to go back to the red rover analogy. I've used this one with you guys before, I think, right? So imagine in the game of red rover, all of the kids are carbon dioxide molecules. Okay? And they are going to try to trap infrared. So carbon dioxide gets in a row and they say, red rover, we call red light over. Red light busts right through because carbon dioxide doesn't capture red light. Carbon dioxide gets up in a row again and says, red rover, we call microwaves over. Microwaves go right through because carbon dioxide doesn't capture microwaves. Fine, that's not the point. Red rover, we call infrared over. Stay with me. Well, infrared gets captured by the carbon dioxide, right? It gets absorbed. It causes carbon dioxide to vibrate more. Because carbon dioxide vibrates more, it causes this carbon dioxide to vibrate a bit more, which causes this one to vibrate a bit more. And now heat is being produced. But here's the question then. What happens if we add longer links in the chain here? What if there's more kids here for carbon dioxide? Well, once you've captured all of the infrared, does it really matter if you have more kids of carbon dioxide sitting right here? Can I phrase that again here? This is really important. So I need your attention, please, because I know I'm talking for a long time today, but I need as best a focus as you can have here. Okay. Let's say that we added another kid over here, and there's another kid over here. Once we capture all of the infrared radiation, does it matter whether we have more carbon dioxide molecules sitting over there? Because that's what this graph right here shows. Okay. Carbon dioxide can only absorb this section here, this section here, this section here, and this section right here. Once those have all been absorbed, what would happen if you added more carbon dioxide? Well, the theory would be that those carbon dioxides would just be sitting there going, I don't have a job. Can you get what that analogy is going here? This infrared, these 2 carbon dioxides, sure, they'll capture it. But what about this kid over here? They don't have an infrared to capture because all the rest of the infrareds have already been captured. So that is the question. What is going to happen? What is going to happen if we keep adding carbon dioxide to the atmosphere? The greenhouse effect, I'm not debating that one so bit, but this is what current climate scientists are working on as well. What happens next? I'd like to share some of this with you. It's called bandwidth saturation. Once all of the infrared that carbon dioxide is able to absorb gets absorbed, the remaining carbon dioxide is just kind of sitting around twiddling its thumbs in a way. And here's some of the empirical proof for it. If you're wondering, Chris, back that up with some experiments. Here it is. Here is a graph that talks about what happens when you have no carbon dioxide. And what you'll notice is that here is all of the different bandwidths of radiation right here. Well, as soon as you put 10 parts per million of carbon dioxide in, all of a sudden there's a little bit of a missing section here. Can you see this little missing section right here? that missing radiation is the radiation that was absorbed by carbon dioxide. This missing section right here is what carbon dioxide absorbed. But here's what's fascinating. Take a look at 100 parts per million and 1,000 parts per million. It was supposed to be right here, and it dropped down to here. Well, now it was up here, and it dropped again, it dropped again. How much did it drop by in terms of like the Y values? It actually didn't really change all that much. Because those carbon dioxides, they've already captured all of the infrared. Let me go back to the IR, to this picture right here. Imagine that carbon dioxide can capture, on a scale from 0 to 100, let's say that these guys right here can capture all of them between 70 and 80, all of them between 40 and 45. Remember how there were like 4 specific bands that they could capture? So let's say 40 to 45 can be captured, 70 to 80 gets captured. Well, once all the 70 to 80s get captured right here, there's nothing left for the rest of the carbon dioxides to occur. Except, here's how bandwidth saturation works then. Rather than only 70 to 80 being allowed to capture, it kind of opens it up and allows 65 to 85 to now become captured. And what you'll notice is that this little section right here is now becoming wider. Do you see how the width right here is changing? So there was only a small frequency that was allowed to be absorbed. Once you run out of that frequency, the rest of the carbon dioxides, rather than twiddling their thumbs, more of them say, well, if we can't take from 70 to 80, I'll start absorbing 81s and 82s and 83s. Okay. So does that mean that adding more carbon dioxide doesn't do anything? No, I'm not saying that at all. Adding more carbon dioxide does have an effect, but it may look more like this. Girls at the back, I've kind of looked your way about 3 or 4 different times, please. Okay, I don't want to have to split you up. This I want you to see. Carbon dioxide has its most effects when you first start adding CO2 to the environment. But as you add more and more and more CO2 to the environment, it has a diminishing effect. Does that make sense? Because after the first infrared has been captured, the rest of the carbon dioxides don't have a job. So they start to widen their scope, the net becomes wider, but there's not more of them to capture. Which leads to this question here. Are we actually focused on the right problem? We focus on carbon dioxide because carbon dioxide is by far the most common greenhouse gas. And we can see this graph go up. And most people see that graph, and unless they had a science teacher who explains to them that that graph is not enough to be considered science, they go, holy smokes, we got a problem. But the empirical evidence is starting to suggest that, well, maybe the carbon dioxide isn't as much of a problem because there are other greenhouse gases that we have to consider. Remember how I talked about isolated systems, like controlled, manipulated, responding variables? Oh, I missed something here. Carbon dioxide is not the only greenhouse gas. There is methane, nitrous oxide. And the one I want to show you here is water vapor. Water vapor, which you might think is completely harmless because you're like, water, that's good for us, right? Water vapor is actually one of the worst greenhouse gases. Take a look at the same chart here. Remember how carbon dioxide can absorb wavelengths in 4 main locations? Those are the 4 locations that carbon dioxide steals infrared from. You keep adding more carbon dioxide, it widens the band, but it can't go any higher than 100%. Does that make sense? Once you've stolen 100% of that radiation, there's no more to steal. So you start widening a little bit. But look at water vapor. Water vapor absorbs here, and here, and here, and here, and a large section here. Water vapor has way more frequencies that it can absorb radiation in. Okay. 2 of the most common potential greenhouse gases are water vapor and methane. They are very potent. But we sometimes ignore these gases because they're less common in the atmosphere. Carbon dioxide gets a bad rap, and it should. Carbon dioxide directly contributes to the greenhouse effect. But water vapor and methane may have even more of a problem. And one of the reasons why is that both of these things have what's known as a positive feedback loop. Okay. We've been talking about causation. Causation is where A causes B. A positive feedback loop is a really big problem. A causes B, which recauses A, which recauses B, which recauses A, which recauses B. We call it a spiral sometimes. Okay. Let me give you a couple of examples of things that we're starting to recognize in the climate sciences as being a problem. One is water vapor. Water vapor is able to exist in the atmosphere more at higher temperatures. This is one thing we're discovering. Have a higher temperature, it means there's more water vapor. But what does more water vapor do? It re-increases more temperatures, which then means there's more water vapor, which means there's more temperatures, which means there's more water vapor. See, that's a bit of a problem. If you can put more water vapor in the atmosphere at higher temperatures, and if water vapor can absorb a lot of different radiations, then you create a cycle. Here's another really bad one, methane. We've discovered there are methane deposits underneath polar ice caps and glaciers. What happens if those polar ice caps and glaciers melt? The methane gets released. What does that do? Well, now methane causes more global warming. More global warming increases the temperature, melts more ice. What's underneath more ice? More methane, causes more temperature increases. Right? And so some science researchers are now starting to consider not only is carbon dioxide an issue, and we still have to consider how are we going to get rid of all the carbon dioxide we've already put in the atmosphere, but what about these other ones? What about these two? And that's what this slide right here tries to talk about. CO2 is not a controlled variable. It gets all the bad rap, and like I said, rightfully so. It's not like I'm disproving it, but I want to have a deeper conversation. I'm curious as to whether this was inevitable. Here's a couple other things that contribute to changing temperatures. You guys remember the word albedo at all? I don't know that we talked about it a ton. Albedo is how reflective a surface is. We make a lot of our infrastructure now with black asphalt, with concrete, with buildings. You know what those things do? They absorb. Black is the absorbing color, white is the reflecting color. As soon as we no longer have a field out here in the winter, snow can cover it. A building, what happens to the Earth's rays? They get absorbed. If this field had no school on it and there was snow covering it, more of the sun's rays would be able to reflect. Does that make sense? Just because we have more urbanization and we're creating more buildings, we're probably increasing their albedo, which means that there's more absorption than reflection happening. Here's another interesting one. There's algae in Arctic seas. Algae are some of those like little micro creatures, you know, like pond scum kind of stuff. They used to just green because they photosynthesize, and most things that photosynthesize are green colors. Okay. Well, as Arctic ice recedes, as Greenland becomes less ice and more green, Greenland's actually ice. You guys know that? It's not actually green. Yeah. Anyways, as the ice on Greenland recedes and more algae starts to grow, you would think, hey, that's good. Life is good. We want to have nice green growing things. But hang on. What color are they? Green. Compared to ice, which was white. White ice reflect. What does green algae do? Absorb. Maybe not a ton, but more than it used to. It furthers the problem. There's a couple other problems here that I'm curious as to whether or not this was inevitable. Our population has increased exponentially. There are more than 7 billion people on our planet now. What does every one of those 7 billion people do every day to contribute to global warming? What happens when we breathe? We output more carbon dioxide. Now, the good news is that trees reverse this process, right? Trees take in the carbon dioxide, but that's one problem. Also, those 7 billion people, we now live in a globalized world. I don't mean to go too social studies on you, but in a globalized world, we like to travel to other countries. We talked about air travel being a problem. Here's another interesting one. We like Amazon Prime. I read a great article. Well, okay. I read a great article a couple days ago talking about how Amazon Prime may be one of the single worst contributors to global warming because of the fact that it's so inefficient. Everyone orders all of their stuff in like small little bunches, and they order their packages that show up with 1-day delivery in the States, 2 days in Canada. It used to be that if you wanted to go shopping, you had to wait for your weekly or monthly shopping trips. Now people just get it any day they want, right? I want to have something new, it'll show up tomorrow. Walmart has this new initiative in the States. This one's crazy. Rather than you going to the store to get groceries, you give them a key to your house, and they will come to your house for you. Have you heard of this? Walmart has a program where you give them a key to your house. They wear a body camera so you can see that they didn't steal anything. And they literally go to your fridge, and they stock your fridge for you. Globalization. Okay. I got to keep going, though. Please stay with me here. This is a picture here. This is a picture here of apartment buildings that I believe comes out of India. Now, India is a very hot country. Like 30 degrees would be a nice, cool, living in India, people would probably like to have air conditioning. I would. I don't like hot temperatures. I'm not conditioned to them. Air conditioning. But what does air conditioning do? It takes all the hot air and pumps it outside, which now further makes the problem worse because now we now get to live in a nice climate-controlled environment, but we're pumped all the hot air outside. Okay. The point I want to make is that it's not a controlled environment when we're talking about carbon dioxide. Yes, the science, the theoretical, empirical science behind carbon dioxide causing temperature changes, that is very true. But the point I want to make is that if you're going to be making political decisions based purely on what's involved with carbon dioxide, I think that's very short-sighted because there are many other factors we have to consider. And if all we do is a carbon tax, we're probably missing the point. I'm not saying that we shouldn't do that, but there's more. Here's even further causes. Now again, don't forget, correlation and causation are different from each other. This is just a graph. But look at this graph. It's a connection between solar radiation and daily temperatures in Mexico. And what we notice is that as the temperatures go up and down, maybe that happened because of the amount of radiation that came from the sun. Maybe. This is just a graph, though. That's not science, but very interesting. Going up over this. But this particular graph, this came from the IPCC, by the way. Like, this is the international governmental agency. There are 4 volcanoes that they made a note of. Check out what happened to the temperature after every volcano. It went down. It went down. Temperatures went down. Temperatures went down. There may be a link between volcanic activity and temperatures as well. We haven't had a lot of volcanoes erupting. The most recent ones are well before the year 2000. It would be a piece of the entire thing. This does not disprove global warming. This does not disprove the greenhouse effect. These are things we should talk about. Hopefully you'll agree on that, right? This is stuff that needs to be pointed out and shouldn't be something that we're afraid to look at because all of a sudden the whole house of cards of climate change is going to fall down. But it needs to be pointed out that there are other factors we need to research. So that leads to the question, so why are there climate change deniers? Right? There are people who say climate change is not real. They stand really firm to that. Sometimes we say, you need more education. And maybe you need the right education because I think there's lots of people who maybe teach things poorly to try to make a point. I did some research. I was curious. Why do people like to deny climate change? So I did this little test here, and you're welcome to replicate it yourself if you like. I went to Google, and I typed in climate change hoax. Here's what I discovered. The top few articles here weren't actually information about why people don't believe in climate change. They were actually the opposite. Google's number 1 and 2, and I think 3, the top hits on Google were not about why people believe, why people disbelieve. They were actually rebuttals. This is NASA's argument as to how we know. And skepticalscience.com is actually a website devoted to proving why global warming exists. There actually were no results in the top few that explained to me when I wanted to research why people were skeptical. I then went to a different search engine. This one's DuckDuckGo. Yeah, is that what your question was? Oh, okay. DuckDuckGo. And the first one that came up is top 10 reasons why climate change is a hoax, or climate change is a hoax. Unfortunately, controlling the message is becoming more and more of a thing, a very political thing, where I don't want to go all tinfoil hat conspiracy thing here, but there have been other rumors of Google choosing to control what search results come up to try to keep information or present other information. And I find that really frustrating because I don't actually believe the hoax, but I want to know why other people believe the hoax, and I couldn't find the info on Google. I had to go to another search engine. I think that's a problem. Go ahead. Yeah.
If you search up the top 10 lists for yourself on Google,
Yeah.
it'll actually give you help.
Yep.
If you do it on free, it'll tell you like the best results.
Exactly. That's a great example. Thank you for sharing that. I mean, it's not something that I'm hoping anybody needs to look for, but therein lies the question, is it Google's job to regulate information? If I want to research why people deny global warming, I'd like to be able to find that. And although I hope that no one wants to try to find a way to kill themselves, that same sort of logic still applies though, right? Does that make sense? I think that is one of the reasons why the global warming hoax starts to take off is that people, in their well-intentioned ideas, maybe make things worse. Here's another one. This is a graph that came out many years ago. It's known as Michael Mann's hockey stick graph. And on the side, I'm putting data manipulation, because here's how the history behind this goes. Michael Mann was researching things like tree rings, ice cores, coral reefs, and historical records, and he plotted this all in blue. So this was the temperature over time. And you might notice that it actually looks like maybe the temperatures were going down. And then the year 1900 came around and temperatures spiked. Now, what also changed in the year 1900 is that we had more thermometers. And so we added a second data set. In red, he had thermometers. And you can see that the thermometers spiked as well. And even further, the thermometers spiked even further. Here's where the controversy came from. Take a look at the ice ring data. Yes, it spiked right here, but right here, the trend seems to indicate that the blue line was maybe on its way down. Here's what made that so controversial. He just decided to stop recording that data. Is that ethical? To all of a sudden be like, ooh, I don't like where this is going. Let's stop. Let's take all my research that may not prove the point I wanted to prove. Let's crumple it up and throw it in the garbage. I think that's poor science. I don't think we have to be afraid that because a couple of ice core data go down, that we can't explain that. Because, I mean, the thermometers are still going up, right? We still have great theoretical explanations for why carbon dioxide increases temperatures. But this became really controversial because of data manipulation. Is that fair? We watched that YouTube video yesterday about what they called ClimateGate, where the scientists had their emails hacked. And basically the exposing, I don't know exactly to what degree, but people were concerned that scientists were manipulating the data to prove what they wanted it to prove. Also, maybe in the vein of trying to control, but maybe making things worse. And if not making things worse, definitely not being ethical scientists. Okay. Here's another one. This is a Bill Nye video that I want to criticize. Okay. I think that Bill Nye is trying to explain a physics principle here, and I think he's trying to manipulate you, and I'm going to try to explain why in a second here. Let's watch it first.
Look, the water level went up.
Okay. So a couple thoughts here. Before I get into my beef with why Bill Nye did this way, I want to point out something. The physics principle behind water expanding when it's heated, that's very true. We can prove that many times. In fact, this does prove this. I feel like he has exaggerated this, though, to make it seem a lot more extreme than it is. Okay. I want to focus on one little thing he said that you might not have caught.
It's rising because it's expanding. Water expands when it gets warm.
I agree.
You can try it. Get a glass, or better yet, a flask.
Okay, pause there. He said get a glass, or better yet, a flask. Here's my beef with this. The type of flask that he used here was round, with a very, very narrow neck to it. He's using this particular flask to really make it obvious why the water level rises. But if you'd have just put this in just a normal size cup, I don't think the effects would have been quite as much. That makes sense there? One more reason why I don't like this right here. Because again, the physics principle is not wrong, but I'm worried he's exaggerating it just a bit to really emphasize his point. Why did he pick the rounded shape? Because the Earth is also a rounded shape. And where's a pen here? I'm just going to draw something right here. I had this earlier today. Here's the rounded shape of the Earth. Now, with that flask right there, he's got water everywhere, right? The entire flask is made of water. But is our entire Earth made of water? Not only consider it three-dimensionally, here could be like, say, the core of the Earth. And then there is water on the surface. Oh my goodness, spelled water properly. Water is on the surface in all directions. Okay. Now, why are these water molecules right here rising up? Here's the explanation of the flask. Okay. As these water molecules vibrate more and more and more, the bottom of the flask is the way they push themselves up. In the same way, please shush whoever's talking. In the same way that as I jump up and down, I am pushing off of the floor to get higher, these water molecules are pushing off the bottom surface in order to get higher and higher and higher. Here's why I don't think this is a fair analogy here. When water is rising, and don't get me wrong, I'm not trying to say oceans don't rise. Ocean levels are rising. Okay? But when the water of the ocean levels is rising, it needs to get pushed off of the bottom of the ocean floor. Do you see how this is not quite the same example right here? Because this needs to push out in these different directions like this. And where does all of the energy from the sun come from? Say there's a sun up here. The sun is going to irradiate just the topmost surface right here. And if the sun irradiates the topmost surface, wherever that surface happens to be, you need to push from the bottom up. Is the energy at the bottom of the ocean floor? Not really so much. But let's say he heated up this flask right here. Where did the energy from the microwave go here? It went in the same thing everywhere here. And so he heated up the molecules that are down here on the floor. Here's why that's not a fair example. The molecules on the bottom of the floor of the ocean aren't the ones that were getting warmer. I feel like he exaggerated this. Now, I think he did it in the name of trying to be helpful. I think he wanted to illustrate a point. I think he did a great job of showing that, yes, heating up water makes it rise, but I also think he may have exaggerated it a little bit. Does that make sense? And where's the line? Where is it fair to do that? Where is it okay to use an analogy that's a little less than perfect? I don't know that that was his intention, but I really do want to call out, he said use a glass, or better yet, a flask. I think he knew that. That's my personal opinion, because I think he wanted to make that point. So that's why I wrote down here, misrepresenting and exaggerating. I think that happens sometimes, and I don't think that's healthy. I think that causes more skeptics. Okay. Here's another one. There are some people out there who I think are looking to make a buck. Often you'll hear the phrase big oil. The big oil companies are trying to make money, and I'm not trying to dispute that. But there's also a lot of money in green energy right now. And I'd like to show you a website. This one is a Climate Reality Project website. And one of the things that irks me about this a little bit here is, I mean, right off the bat, they say the science is settled. Okay, I take a little issue with that right there. I wanted to do some research. I wanted to see, what are you going to teach me, Climate Reality Project, about this? And I found this little spot on the website here where you can get trained, where you can support them. I'll get to that in a second. And there's this spot here where you could spread the facts. And I was like, you know what, I'm a science teacher. I want to be able to spread the facts. And so I had to sign up. I had to give them my email. And they emailed me a document, which I thought was going to be the facts on climate change. I want to show you the document they emailed me here. This is what they sent me. I was looking for, what are the facts behind climate change? And it was supposed to be sent out to teachers. And here's what I got, a document that says climate change belongs in the classroom. And it talks about the climate crisis making headlines, and it talks about how to prepare your kids for the world. But as I kind of kept going through it, I was looking for anything on science that I could use to share with you guys about how climate change works. And the long story short is that there was none of it in there at all. In fact, here was their main point. They want to talk about denying kids the truth. They want to talk about kids learning a lot by taking on climate change. They want to talk about the solutions to the climate change will create many jobs. And I found myself very frustrated because it was advertised, if I can go back here, as I wanted to spread some facts. And if I can be blunt, I got a little bit of propaganda. And here's why I take issue with this website. The big red button at the top right here is what I take issue with. Because just as much as there's big oil trying to maybe prevent and suppress climate change, I want to call this company out here. I think that they're really just trying to get your donations, because that was the next button right here, support our work. I did a little more research into this because I wanted to know more about this company. I discovered that they made $13 million in the last year, including $3.5 million that just came from government grants. And when I tried to figure out what their job was, it was mostly about this. It was about training more people to talk about why climate change was bad, but to not actually teach any science. It was just to spread the word that we need to solve climate change. And I think that also contributes to a problem. Again, I think these guys are trying to do good work, but I think we have to admit that there are people who are trying to make money in the oil business just as much as there are people who are trying to make money in the green energy business. Does that make sense? So wrapping up my lesson, I'm getting here. So what do we take away from this lesson here? Because this is a deep and very involved lesson. I'm not covering this superficially at all. I'm trying to show you as much as I can. Here's, I think, my summary here. Predictive models are still a work in progress. And that's a normal thing in science. We're asking science to tell us what the future holds for us. And scientists are still trying to figure that out. Here's a graph of temperature changes over time, along with the predicted temperature changes. Just because the actual temperature and the predicted temperatures don't match doesn't mean we need to say climate change doesn't exist. That's not what we're saying at all. Here's another one of these ones here. Here's some predictions that the IPCC gave for years. We've talked about how they've been working on this since 1990, 2007. Here's all of their predictions, and in blue, here's what actually happened. Did any of them match exactly? Well, I mean, to be honest, actually, they all did at one point, didn't they? Check this one out. Yellow matched right here. Red matched right here. Brown matched right here. I think most people would probably look at it and go, well, but where we are right now, it's not really real. But that's why I want to come back to the nature of science. It's okay that our models aren't perfect. They're not supposed to be 100% yet. Here's another piece of evidence that some people like to talk about and argue as either, here's why global warming does or doesn't exist, and it's just one little piece. Here's a picture. This came off of NASA, by the way, who takes all these images from space. Here's a picture of where Arctic ice used to be. It used to be all the way out here in the yellow line, and you can see that it is clearly, there's ice. We are losing Arctic ice. Proof of global warming, they say. Well, yeah, another piece of evidence. But what about this? This is Antarctica. And I've got the quote on here from them if you want to read what they said. But look at this. Antarctica actually has growing sea ice. That doesn't seem to make sense. Why is there more ice growing at Antarctica? And it could be stealing. It could just be because science, we still have more things to learn. We still have to figure out exactly what is happening there. Okay? Here is the timeline again of chemistry. And the point I want to make out here is that when Rutherford or Thomson, when they discovered something new like the nucleus, I don't think it's fair to say that Rutherford was a subatomic particle denier by asking hard questions. That's what I want to get at here, is that scientists are supposed to ask hard questions. They're supposed to challenge each other. And when they see something like this right here, they're supposed to say, whoa, we got more to learn. Just like we have more physics to learn, just like we have more chemistry and biology to learn, there's still more to happen. Okay, I'm going to skip this slide because I'm running out of time here. You guys ever seen the movie Back to the Future 2, where Marty McFly brings the sports almanac in the past, and then, what is it, Biff ends up making, predictions? People like to predict the future. I found this scientific article. Check out this title here. They want to be able to predict NHL match outcomes using science. They want to try to figure out a way to make predictions about who's going to win an NHL game, somehow using some sort of science analysis. And they've got previous research in here where you actually can see, I know it's small here, but they talk about in the past, they were 75% accurate on the World Cup. They were 78% accurate on the NFL. Right? People like to be able to make predictions for the future. There is nothing wrong with that. That is supposed to be part of science. I think this is a really good summary slide for where we're supposed to end. This is a scientist. He comes from the University of Montana, not that far away from where we are here. His name is Dr. Harper. And he just got back from a week-long Greenland trip he did in July. And they did a 5-year study on glacial motion and effects on melting ice. I just want to share with you some of his quotes, because I feel like this is what good, healthy scientific debate should look like. Here's his quotes. They came from different articles, by the way, just fair disclosure. One quote. We're looking at the water underneath and how it influences the motion of ice sheets, he says. The more water you put down, the faster the ice may move. It's speeding up. That's what we're trying to figure out, is how fast it's speeding up. You see, he doesn't say that he has all the answers. He says, we're trying to figure out how fast this is changing. And I like the second quote here. We simply don't understand the physics of ice dynamics well enough to make accurate model predictions, says Dr. Harper. There's just too many uncertainties. Because we're still trying to figure this out. That's why scientists are getting grants to go for 5-year studies in Greenland and look at ice up there. So here's my summary. Here's why climate change is such a difficult, divisive, opinionated topic. Our challenge is that we have to now make decisions in the present which affect our future, but the scientific process is not finished yet. The scientific process will never be finished, and yet if the guy is right about the world coming to an end in 10 years, we have to start making a call now. How do we do that without science fully finishing things? So here's where I'm going to end here. Thank you guys for staying with me because this is a long lesson, but I hope this was valuable. We're going to do some research now. I'm going to have you guys break up into groups, and we're going to research some possible solutions. I don't know that any of these are the solution, but these are ideas that humans have. I'll walk through them real quick, and then we'll take off for lunch. First one's a carbon tax. Very unpopular in Alberta. The idea basically being that we put a price on carbon dioxide emissions. Another one is called carbon sequestering. Saskatchewan is really big into this right now. They're trying to pump carbon dioxide out of the atmosphere and put it underground. Very promising, very expensive though. New energy sources. The idea of investing in nuclear and solar power is another possibility because we need to, in theory, we need to try to become off of carbon. The Green New Deal is another one we talked about in the video yesterday. I'll have a group research that. There have been international agreements like the Kyoto Accord, the Paris Agreement is a more recent one. I'll have a group look into standard of living reductions. The idea that we may need to give up our cars, our cell phones, our air conditioners, our heaters. As soon as we start having that conversation, people start shaking their heads and they go, ugh. Here's another interesting one that only started to happen recently. What about climate strikes? Keeping an open mind. Here's another one, emissions credits. I talked, I think, with one class about Justin Trudeau. He had 2 airplanes. Did I tell you this story? And how he justified the use of a second airplane by buying carbon emission credits. Anyways, I'm going to have you guys do some research into these topics, and you're going to present to each other in small groups whatever you've learned. So since I'm basically out of time today, why don't we end that there? But that's what we're going to spend the next couple of classes on is, now I'm going to give you guys time to go do some of your own research. Okay, 2 passing thoughts. Thank you for staying with me for such a long lesson. That was a ton of information. I hope you found it valuable. I hope you think that I was fair and balanced, that I really approached the science. I don't want anyone to come away from this saying Chris is denying anything or is trying to put, I want this to be science focused. Okay. Number 2, just a quick reminder, please don't forget to keep doing all of the tasks on Moodle. There is a reflection that you can write after this lesson. And there have been reflections as we go along. Don't forget about those, okay? So the H word, if you haven't been doing a little bit of homework here and there, maybe double check Moodle and see whether you're falling behind on anything. I don't really assign homework in this class, but maybe just remind yourself, we still have stuff to do, right? So there is a reflection, and there are questions that you can answer after this lesson, okay? Okay, I'm done. You guys can pack up. Thank you guys all so much.